You have to show. Okay, now why G is non-trivial? Lava?
Yes, bro.
Suppose G is simple abelian. Okay, why is it non-trivial? Okay, this is the theorem. An abelian group is simple. You know how to move. So you know how to use zoom. You can move the, let me show you. Wait, what happened to my zoom? Guys, don't mind that. There is a bar. There is a bar in between the faces and the screen. You can move, so you can see my writing bigger than the screen. I don't know how to share that. Share Zoom in Zoom. Anyhow, you can move that, okay, and you can pin me, right? You can play around with the view if you're not used to Zoom. There's a view on view, right? Right top, right? And you can click that. You can do speaker, side by side speaker, like that. Or you can just do standard. Otherwise, you will see very small. Or if I pass the host to Hannah, you can spotlight too, right, Hannah? Okay, you can help them. Okay, go back. Because I need to see both, yeah? Okay, so, all right. An abelian group is simple if and only if it is finite and of prime order. Okay, so you go this way, yeah? Okay, suppose G. When you say suppose G, so we want a group to be G. Suppose G is a simple abelian group. Okay, you assume G is a simple abelian group. Then why is it non-trivial? Then G is not. G is a non-trivial group. Why? That is my question. Why? Somebody want to try answer that? Because why?
Because the order of G is 1, 1 is not prime.
Okay, that is what we want to show. We haven't shown that yet. Okay, why it cannot be trivial? If it is trivial, it is not simple. Because that's the
symbol.
what's the proper
Definition.
Yeah, it's by definition. It says by definition is a non-trivial group.
Because J is simple, so not trivial, not has a trivial group.
What if G is E? If G is E, the only normal subgroup is the trivial subgroup or itself. There is no proper normal subgroup, right? So G is, this is the improper normal subgroup, right? Understand? This is by definition. Okay. So we want G to be simple abelian group, right? Now we want to show G is finite. So since this is not trivial, so you have G, you have the identity element, right? So show G is finite. Let G not equals to E. Let G not equals to E in G. Okay, let G be a non-identity element. Now let H be a subgroup of G generated by this little Z. Okay, let H be a subgroup of G generated by G. Since G is abelian, so H is, thus H is normal in G. Right? Since G is, okay. Suppose we prove by contradiction. Suppose the order of G is not finite. We want to show that G is finite. So suppose it's not finite. Suppose it's infinite. Suppose the order of G is not finite. Finite is this. Finite is this. We don't write equal infinity, right? So not finite. Suppose the order of G is not finite. Then you take the square of G. Okay, the square of G is also a proper normal subgroup. A proper normal subgroup. But this will give, okay. Oh, this one I forgot to write, right? Since G is simple, G is H, right? You cannot have proper one. Okay. If you have an element G in G, you generate that, you get a proper subgroup. It has to be normal because it's abelian. But since G is simple, you cannot have the proper normal subgroup, so it has to be equal. Okay, so we don't get the proper one. And suppose G is not finite. If it's infinite, we can take the square of the element G, and this becomes a normal subgroup since G is abelian. So a contradiction, since G is simple. contradiction to what? Thus, G is finite. Okay. Now, that is the first part. And then the next part is to show that the order of G is P. Okay. Oh, suddenly it's so hot. Apa? Part? Okay, so now next one is show that G is of prime order. Next one. This is just still one way. Okay. Suppose, oh no, show the order of G is. Okay. Now we want to prove by contradiction. Okay. Suppose the order of G is, what do you use that? Mn. Okay. I don't want to use P, I use K, is M times N. Okay, a composite order. Okay, composite order. M bigger than 1, N bigger than 1. Okay, like 12 is 3 times 4. 12 is 2 times 6. Okay, so composite order. Okay, then then you use, okay, this one, we want to take the order of G, small g. Let me go back to the original. Since G is simple, we have the group, subgroup G, right? The subgroup G. I call this H earlier. Let me go back to the one before. Okay, so we know that this is actually G. You cannot have a subgroup because a subgroup will be normal of an abelian group. We cannot have a proper normal subgroup since G is simple. And then we square the G, right? And then this is a proper one, which is impossible. So we have the order of G. What did I put just now? If it generate the whole G, it has to be also finite. So we assume the order of G is finite. And since just now we get this equal to, right? Cannot be a subgroup because we cannot have a proper normal subgroup. So the order of this is order of this, which is finite. Okay, this is before, right? I want to get it straight that the order of little g. Okay, now when I made this one, to be consistent with that one, okay, we want the order of G, right? We want to show that the group G has prime order. Suppose this G has composite order. Okay, now we take the, what is that? Oh, M times G. And you put GM, you see this K, M, N, they are in Z plus. Okay, because they are orders. Yeah, they are numbers, orders. Orders cannot be negative, the order of an element. Okay. So when you multiply this, don't get yourself confused. G is the element, M is the integer, positive integer. All right. So if you assume like the order is 12, this is like 3 times 4. You can take any one of these, multiply by G, and this is a subgroup of G. And since G is a billion, it's normal. Okay, so this is a contradiction because G is simple again. So P must be prime number. So not only the order of G is finite, it has to be a prime number. Okay, why am I explaining this instead of okay, next.
Prof,
Yeah.
Prof, I want to ask, for the GM that Lava put that, shouldn't it be G to the power of M?
No, this can be a multiple
Oh, okay.
of G. It
Can it
depends.
be to the power?
It can be, okay, if the group is in general, like just now is G squared, right? Yeah, Lava?
Yes, Prof. G square. Yes, it's G square over here.
G squared, right, before?
Yes.
And what about this one? G to the M.
I think it's a typo. It should be G to the power of M.
Because if you have like this, then it's mg. Okay. If you're using any this, it'll be like this. That's why it's on the right, right? Because it's supposed to be the power. This is chapter 3 in the last class, secret groups. Okay, if you have one element in the generator, then you take power of other elements, it becomes the other subgroups, if you remember. Okay, so using this idea actually, right? So if this is not any of this, you take any whole power, it becomes the whole group, not a proper. This one is proper, it's not the group. That's why it has to be the prime. Any other question? Okay, go down.
Excuse me, Prof.
Yeah.
Can use Cauchy theorem to prove this part? Cauchy theorem.
Cauchy theorem says that
FB a prime number, which is the device of order the group, has then the group has a subgroup of order B.
yes. And how you use this for the proof? If the order of the group is, you want to show it is prime.
Yes.
Right? So you want to show it is prime. This one, if it divides. Even if this one, okay, is it that P? So how are you going to use this Cauchy theorem?
Can I share proof?
Yes, sure. If just now you haven't finished yet, Lava, okay, you can stop sharing because you don't go the other way around, right? Okay.
Let M be the order of G.
Okay.
By Cauchy theorem, if B the prime number, which is the divisor of M, then G has a subgroup of order B, but G is simple. Then M is prime.
Okay, then if let G be the order of
order M. Yes,
Okay.
M.
And
The Cauchy theorem say if B is prime number, which is the divisor of M,
okay.
then G has a subgroup of order B,
Okay.
but G is a symbol.
Yeah. But do you know H is normal?
Yes, no, normal subgroup.
Because G is a billion, right? So
Yes.
let P be a billion of order M. So if P divides the order of G, then there exists a subgroup of order P, right? Is that what you're saying?
But G is symbol. Give B is a symbol.
So what?
But G is a symbol. G.
G is simple.
Yes.
G is simple, right?
Yes.
So a contradiction to what?
Then M is prime. M equal to B, I think, by contradiction.
Oh.
Huh?
No, contradiction to what?
No, M is prime then. Then M is prime.
M is P.
Yes.
But you said if P divides the order of G, which is M. So if M is prime, P, you said P divides M. Doesn't say anything. Because, like this, right? Prime, right? So P still divided, this is not prime. It doesn't need to be. Right? But if this is prime, it's the other way around. If G is prime, then if M divides G, then M is 1 over P. You see? It's the other way around. The other way around is not true. If a prime divides the order of the group, doesn't mean the order of the group must be prime. It can be P times. You understand?
Yes.
Yeah. So this one doesn't mean that M has to be prime. Because a prime can divide a non-prime. But if you divide a prime, if you divide M, if you divide a number with a prime, like 7, right? K must be 107, right? So if prime divide a number, like 7 divide a number, this can be like 14, right? Doesn't have to be a prime. So I don't see you can use for this one. Okay? You can stop sharing.
Okay.
So I don't see you can use that. Maybe the other way around. This showing the other way around. So you can rewrite your properly how to use Cauchy. If it is prime and finite, then you have to show that the abelian group is simple. If it is not simple, then it has to have a normal subgroup, right? But since it is prime, since the order is prime, you don't have any proper normal subgroup. You see, this way is much easier, right? Suppose G is P less than, this is what I just explained just now. Suppose G is prime order and finite. G abelian. Okay. If let's say assume H is a subgroup of G, it has to be normal, right? Because it's abelian. Then the order of H must divide, right? Since this is P, so H is this or this, right? Because nothing else that divides prime. The order is 1 or P. So if H is this or this, thus G is simple. Okay. I thought I give this as exercise, right? Now I cannot give assignment number 5. It's already okay. That's why I put exercise. Okay, Lava, it's your fault. So this is the other way around. I think, can you share again, Lava? Because I didn't see this part in your sharing just now. Is it right? It's not in your sharing, right? Yeah, this is only that way. What about the other way? Okay, that's okay. Go next. Okay, 2 odd tests. Okay, suppose G is a group of order 2 times n. N is odd number greater than 1. Then G is not simple. Okay. Okay, so let the order of G is 2 times m and odd number. I use m, right? Okay, and we want it bigger than 1, right? Then G is not simple means there is a normal subgroup, right? So what we do is you show this by showing the silo theorem. Okay, like 40 and then you write as silo theorem and you find the number of silo subgroup, right? But this is just an example. It is not a proof, right? Lava, is that clear? This is just an example. Okay. Anyone else has a proof or found a proof? Can you share? The one that you shared just now is order, what was it? 2 cubed times 5? 40?
Order 40.
40?
Yes.
Okay, 40 is 2 times 20. Okay, it has to be 2 times odd. Okay, anyone else get the proof? If not, I'll give you more time to find it. Then we can. Farah, did you have the time to find or no?
I tried to prove it, but I can't. But I get the idea. I know I have to use the silo, but I don't have the idea of how to prove it using silo actually. I've been asking Hannah as well on this part.
Because if you use silo, right? Okay, let's see. You know that the order of G has to be even, right? Because it's 2 times. So the order has to be even. 2 times odd is even. And you know odd number, they can be a prime or they can be a composite, right? It can be a prime, it can be a composite. So if M is a prime, so it's 2 times a prime. If 2 times a prime, so the prime can be 2 also, but odd number, so odd prime, right? So if it's a prime, then you can have the silo, right? So you have silo 2 and you have, you have silo 2 and then you can have silo prime, right?
P.
Okay, if M is a prime, definitely. Okay, and then what is the number? Like 2 times 3, right? So the one with the silo 3, then you will see that is the one that is normal. Then it is not simple. Okay, what if M is a composite? Like the number right? 2 times 105, right? Is that 105? No. Yeah. Yeah. Right? This is a composite. So the original is the order of G is 210, right? It's 2 times 105. 2 times 105 is an odd number. But this part is composite. It's not prime. But it's a product of primes. I can have 2 over here. Still, it's a odd. So how are you going to use silo? Right? Because you don't know composite is how many. If you want to use silo, the only thing that we know definitely is silo 2. But silo 2 will have many number of silo subgroups, right? Remember when you do even 30 or 6, even in last class I mentioned about S3 of order 6, it has 3 silo 2, right? So the silo 3 is the normal one. In that case, you cannot choose the silo 2. Okay, it does not say that definitely one so normal. And you have silo 3, silo 5, silo 7. So for this one is okay, but this one, how do you determine the silo? Because you have different primes, not only just one. Because odd number can be composite, right? Prime, right? Because it says odd number. It didn't say this is prime. You see? Okay, maybe some of the others have not found or tried. I let you to continue trying. If anybody has already approved, then you can share. I can help explain. Farah, is that? You understand that?
Yes, actually, I Googled about this question, and some of the proving they use isomorphism. Is there any other way of proving this without using isomorphism? Actually, I try not to use isomorphism. Most of it, they are using isomorphism to prove this theorem. Actually,
Because sometimes there's only one way to prove it, or the other way is too difficult or too long. Okay, did you have it written down?
no. I tried to do the silo part only, but I didn't
Okay,
manage to finish it.
I don't think you can use silo for the second one. For the first one, it's okay.
Okay.
Okay, we'll leave that first. Okay, you hold on to that. Maybe the others have not had the time to look at the proof. So the others, I don't want to just give everything. You need to try and see how far you can understand. Yeah. Okay. The next one is, you cannot find index theorem, you said? What about 1.6? Anyone is successful? The dividing the index factorial. Did you find it, Hannah?
Yes, Prof. But I'm not sure is it correct or not. But I can just share my screen.
Yeah. So this is by group homomorphism. Why sometimes or many times they use group homomorphism to prove? Because if you use kernel, as we mentioned in chapter 8 last semester or undergraduate abstract algebra, kernel of an isomorphism or automorphism is normal. It's a normal subgroup. And G modulo the kernel by isomorphism theorem is isomorphic to a subgroup. So the order of the group G to the kernel, to find the factor group, the G mod H has to be normal in the first place to find the order of the factor group, right? So G modulo the kernel. So in this case, by this mapping isomorphism, you have that this has to divide. S is G modulo H is given as S. Okay, that is an idea by using the automorphism with the kernel as the normal subgroup in the automorphism. Okay, I will let the others to look at it first. I'm sure not all of you have looked at this. Okay. Next one, I will continue with some more examples of simple groups. Okay. The next one, common, very common, is the dihedral group. We look at the presentation of the dihedral group in general, right? Not only for order 8. So dihedral group is generated by rotation and reflection, right? So if A is the rotation and B is a reflection, right? I or E What is the relation? Anyone remember? A inverse
A inverse B equals to BA, I think.
A inverse
B equals to BA.
B equals to
BA,
BA. Is that right?
if I'm not mistaken.
You have your notes. Did you bring your notes or not? Shihab will double check. What chapter is that from last semester? 11? What is it? A? AB squared? Cannot be B squared, it's E. No?
Prof, I've checked mine. It's right.
That is in the exercise. It's somewhere, right? I missed that one. Okay, because this is not unique, yeah? Okay. A inverse is A n minus 1, right? So sometimes B, people put B inverse because B squared is E. So this can take many forms. Okay. All right. So you have to know that a group H generated by B has order 2, for example, right? A subgroup H2 generated by A has order. What's the order? N. Okay, because A to the N is E. So you have to know that the index of this, you have to know that the order of B to N is to N. Sometimes people put N, okay? So it depends. To the authors, it can be N, it can be 2N, but I meant it's the Dihedral group of order 2N. Okay, so this is 2N over N, which is 2. So we know this is basic things that you have to know about the Dihedral group. So H2 is normal in Z. The rotation, the subgroup of rotation, it is normal in Z. Okay, so this is not equal to, we know that D to N is simple or not? Not simple. Okay, so instead of order 8, I do this for the whole of the Dihedral group. All right. Next one is again Quaternion group. Okay, we will take a look again when we do group presentation. Right, we will see this again. Okay. Now, for Quaternion group of order 8, we have also the subgroup generated by I, J, K, right, of order 4. So the index is 2. So all those subgroups of order I, J, K also normal, right? Let me write that. There is also generalized quaternion. And you can generalize this. I just give for Q, right? Okay, quaternion of order 8. So you have the identity, you have -1 of order 2, you have positive, negative I, J, and K of order 4. So the one that I mentioned just now is that this is actually equal, right? And same thing, they are equal. And this, they all have order. What's the order? 4, right? I, 1, 2, and 3. So Q, the index is 2. So this is normal. So Q is not simple. Actually, you just need to find one. Okay, you need to find one. Okay, the next one I mentioned about symmetry, right? And also the alternating group. If you remember the alternating group, can somebody define an alternating group? All even permutation, right? Permutation group is even permutation. So what's the order? If you have all permutation as n, right? The group of permutation, the order is n
Factorial over 2.
So if it is half, the order is,
Factorial over 2.
right? So if want to find the index, this over this is equal to, right? So this is normal in Sn. But only for n bigger or equal to 5. It's simple. What does it mean? The normal one. This is for you to look up, yeah? Why an is simple only for n bigger or equal to 5? Because if you see for less than 5, right? You have seen S1 we don't really see. S2 is just a billion. So if you look at this, 5 is included, right? This is order 6. This is order 24. So there is a normal subgroup here. There is also a normal subgroup here. Look at when n bigger equal to 5. Okay, so I will leave that. Now another question is a group of order 210. Why? Because theorem 1.5 is 2 odd tests. So this is simple. But this is not simple, right? Because this is 2 odd tests. Okay. Another one example is this is not simple. Now I said that suppose H is a subgroup G of order 16. How do I know there is a subgroup of order 16? Anyone? Why? We know 80 is 16 times 5, right? So we know there is a subgroup of order 16, which is the silo 2 of G. Right? And by silo theorem, actually, we can find a normal subgroup for this one, but using theorem, what theorem number? Theorem 1.6. Okay. By theorem 1.6, add that to my notes. By theorem 1.6, since 80 is not a divisor of 5 factorial. Okay, because we want to see G is not a divisor of G mod H factorial, right? Okay, so 80 is not a divisor of, what is 5, right? What is 5 factorial? 120, right? Go easily using this theorem. Okay. Let's take about 2-3 minutes break. Okay. Okay. All right, so that's a very quick 2 minutes. Okay, now it's a maximal normal subgroup. Although I have mentioned about this last semester, we'll review again. A maximal normal subgroup. If you have two normal subgroup, a maximal one is there will be no normal in between, right? That is what it means by a maximal normal subgroup. Let me just write it out. If you remember, this was in the test of final last semester. Okay, now what's the definition of a maximal normal subgroup? Okay, let G be a group and H is normal in G. then H is a maximal normal subgroup of G if H is the largest. If H is the largest normal subgroup of it's just not just in general the largest. It has to have another meaning. Meaning there is no normal subgroup in between H and G. Okay, there might be, when you say largest, there might be two same size normal subgroup but different. There might be two maximal normal subgroups in a group G. Okay, so it is not unique. Okay, I will show you why it is not unique. Okay, now let's go to the easiest one. If I put like this, right? Right? In the series, you remember, there is nothing in between. So this is the largest. Okay, if you have this, this is the maximal normal. This is not, because there's a larger one. This is inside. Okay, now, do you remember Z8? Can you draw a subgroup lattice of Z8? Draw a subgroup lattice of Z8. And then I want you to show me like this. If you can get it quick and scan, also you can share. Hannah, make me your co-host, please. Because, okay, now I can see. Okay. Easy. Who want to share first? Anyone? Shihab, are you done? What is the order of Z8? 8. Okay. So the subgroups have to have order. 1, 2, 4, and itself. Okay. And this is cyclic, right? So you remember, if you have G is Zn, for any k dividing n, there is a subgroup of that order, n over k. Okay, remember? If you have Zn, so it has a subgroup of all devices. For all devices, there is a subgroup of this order, right? So we have order 4. Order 4 will be 2, right? 8 over 4. Okay. Order 4, order 2. Order 2 is 8 over 4 is 2. Order 2. Order 1 will be 0. All right. So this is the subgroup lattice of Z8. This is order 1, order 2, order 4, order 8. All right. So what is the maximal normal subgroup? Maximal proper,
2.
is generated by 2.
2.
Generated
Yes.
by 2. Okay. Now you find for this Z12. So for this one, we have of order 1, 2, 3.
3, 4, 6.
6, 12.
Okay. Now we draw. So you have Z12.
Generated by 2.
Okay, this is generated by 1. And then you have 1 generated by 2, 1 generated by 3.
3.
Right? So 1 generated by 2 is of order 6. Okay. What is this? 1, the whole thing is 12. Generated by, this is 6. This is 4. And then we have 1 with 6, right? And 6 is of order 2, right?
Yes.
And this is under 2 and under 3, right? And then we have 1 more of
4.
4.
4.
of order 3, and then
Then 0.
so now what is the maximal normal subgroup?
2 and 3. Generated
So-
by 2 and generated by 3.
Subgroup generated by 2 and subgroup generated by 3.
3.
All right. So I just put this, some books, because this is of order 6, this is of order 4. They put this higher, this lower, but this is okay, it doesn't matter. This at one level does not mean that it has the same order. Yeah. Some books, they put it a little bit lower. This is higher, they put like this. But it's okay. This is okay. So the maximal normal subgroups for this is generated by 2 and generated by 3. So that is
3.
why I said, when I say it's the largest, doesn't mean this only. Okay, this is the one that there is nothing in between. There's also another one that there's nothing in between. This cannot be maximal because we still have this in between, right? So
Yes.
this cannot be maximal. This cannot be maximal because there is this and also there is this, right? Okay. Okay, now example 110. For the Dihedral group, D8 R90 is the maximal normal subgroup. Okay, that is of index 2. Okay, so just now when I give you D2N generated by A and B, right? So this is the largest normal subgroup, or the maximal subgroup, right? Okay. Just now, I also talk about Q, right? Q. Now it's cold. Okay, everyone draw the subgroup lattice for Quaternion group of order 8. Okay, so you have I, J, K, right? And each of those has -1, right? And 1. Okay, this is 1 -1 I negative I, 1 -1 J negative J, 1 -1 K negative K. So these are the maximal normal subgroups, right? Okay. Okay, and example 112, I have mentioned that. I mention it again for S3. The only normal subgroup, so is the maximal normal subgroup. If there is only one, that is the one. Okay, if there is only one. Okay, that is an exercise. That exercise is exercise 1. Okay, I will just write it, but you have to do it. Theorem 1.7. Even if you refer to any book, any Google for the proof, but when you rewrite, when you write, make sure you understand every single word. Okay, books normally, especially papers, they don't, when it said it is clear, most of the time it is not that clear. So you never write in your thesis, it is clear. It can easily be seen. No, you cannot write that in your thesis. In a paper, that is okay. So when you refer to books or paper, even books normally don't put, but even if it said that, you have to write out for this class, especially for your assignment. Okay, if there is assignment or test, don't just jump. You have to explain every single step and make sure you understand, right? So H is a maximal normal subgroup of G if and only if G mod H is simple. H is a maximal normal subgroup of G if and only if H is simple. So you have to, you see this? So you have to do 2 ways. Okay, so for this one, let G be a group and H is a maximal normal subgroup of G. Then show that G mod H is simple. So the easiest way is to show by contradiction. I'm giving a hint. I hope I don't give you an answer. I'm giving you a hint. Okay. Suppose when you write out, suppose G is a group and H is a maximal normal subgroup of G. Okay. Assume or let or whatever you put there, suppose or G mod H is not simple. You have to show it is simple, but you assume it is not simple. So if G mod H not simple, then G mod H is a normal subgroup, which is proper normal subgroup, right? What is G mod H? Is the factor group, right? Because H is a normal subgroup, you can take the factor group. So if it is not simple, then you have somehow a subgroup right? You have, which is not equal, which is normal, right? Okay, I can put this here. If you have this, I'm giving the answer. If you have this normal, you have to have the K. Normal. If G mod K is smaller, a subgroup of G mod H, then K must be bigger than H. Okay, so you have a K bigger than H, normal. So this cannot be maximal. You write it out, I just give you a hint. I already give like 80%. Okay, that is a hint. That's like, okay, the other way around. Given G mod H is not simple, show H is maximal normal. So again, try to prove by contradiction. Suppose G mod H is simple, then there is no normal subgroup in between, right? And there is no H in between. There is no maximal normal, which is a contradiction again. Okay, so that's a big hint. Just the key is if you have this like this, then this is bigger because this is smaller, right? See, right? So it's the other way around. Like you're dividing something, if it's in the denominator, this is numerator, denominator. If the denominator becomes big, the whole thing becomes small. If you want this one smaller, this one will be bigger.